Okay, hello everybody. Welcome back to Algebraic Topology, Lecture 3. So I want to start off with two things. So today we're starting Chapter 1 of Hatcher's Algebraic Topology. I really don't feel like doing this today, but it has really more to do with me and how much I've been working recently than with the topology, and so I'm gonna try and do this, and if it just doesn't turn out, it just doesn't turn out. I'll probably still post it anyways because the whole point of uploading these things is just to kind of show the process of working through these things for the first time. Like there's all of these like short YouTube videos explaining really big concepts. And while those are great videos and very well produced, a lot of math is taking a long time to think about things. And even though I'm taking a long time to think about things, I'm still trying to do it in a relatively short window of time. Which means that, I need to kind of force myself to sit down and just do it sometimes. Um, and really, I'm not always the best at that, but I want to go for a PhD. And that is a big part of doing a PhD. And I feel like this is a skill that I need to build. And so, yeah, forcing myself to show up. Let's do it. Okay, so today's lecture, the actual content of this video, will be on the fundamental group introduction. So I'll go ahead and read the first part, just kind of the exposition that Hatcher has. So, algebraic topology can roughly be defined as the study of techniques for forming algebraic images of topological spaces. Most often, these algebraic images are groups, but more elaborate structures such as rings, modules, and algebras also arise. The mechanisms that create these images, the lanterns of algebraic topology, one might say, are known formally as functors and have the characteristic feature that they form images not only of spaces but also of maps. Thus, continuous maps between spaces are projected onto homomorphisms between their algebraic images. So topologically related spaces have algebraically related images. With suitably constructed lanterns, one might hope to be able to form images with enough detail to reconstruct accurately the shapes of all spaces, or at least of large and interesting classes of spaces. This is one of the main goals of algebraic topology, and to a surprising extent this goal is achieved. Of course, the lanterns necessary to do this are somewhat complicated pieces of machinery, but this machinery also has a certain intrinsic beauty. The first chapter introduces one of the simplest and most important functors of algebraic topology, the fundamental group, which creates an algebraic image of a space from the loops in the space, the paths in the space starting and ending at the same point. So, he kind of goes into the idea of the fundamental group. And I kind of want to start by explaining what my current understanding of the fundamental group is. So in this series, I've kind of talked about how awesome my topology professor has been, or was when I took topology this past semester. And like he was so awesome. Like I cannot say enough good things about that class. We did actually a bunch of algebraic topology. We got through a large portion of this chapter. Um, and so we didn't do a lot of the examples, but we did do kind of, as far as I can tell, up to the Van Kampen theorem. And so my understanding of the fundamental group is that if you have some topological space, like so, um, and we call it maybe like a based space or something, right? And maybe we put three holes in it. Um, then basically, if we have a base point at this green star, then we can kind of create like classes of loops, equivalence classes of loops. And so a contractible loop is one like this where it doesn't go around one of the holes, and so, it can kind of go wherever, be continuously deformed back to just the base point. And then you have kind of the first class of loops where it's like around one hole or around another hole, or around this third hole. But then you also have like classes of loops which go around two holes, right? And permutations of which holes you go around, um, kind of like so. And then, of course, the loop, which goes around all three holes. And since these are holes, we can't kind of form the loop through the hole, and so we have to kind of give it a different equivalence class in terms of homotopy type. And so the fundamental group of a space is basically just the homotopy class, or like the homotopy class is induced on the space. Um, so with all of that said, let's go into what Hatcher has to say about the fundamental group. So he says, consider two linked circles in R3. And the key point here is that they are linked. Our experience with actual links and chains tells us that once the two circles are linked, it is impossible to separate B from A by any continuous motion of B, such as pushing, pulling, or twisting. At least this is what intuition suggests, and the fundamental group will give a way of making this intuition mathematically rigorous. Instead of having B link with A just once, we could also make it like link multiple times. And so the picture he gives is kind of like if you have something like this. Oops. Where it like links around twice, like kind of coils up. We can basically do this by assuming an orientation of the loop. And so for a non-zero integer n, we have an oriented circle linking n times, where by circle we mean a curve homeomorphic to a circle. To complete the idea, we could let, B0 be a circle not linked to A at all. Where like this is A and this is Bn. Now, integers not only measure quantity, but they form a group under addition. Can we link the group option geometrically with some sort of addition operation on the oriented circles linking B and A? So an oriented circle B can be thought of as a path traversed in time, starting and ending at the same point x0, which we can choose to be any point on the circle. Such a path starting and ending at the same point is called a loop. And we can define loop addition just by saying, if you have two loops and you have a base point like so, if this is loop number 1 and this is loop number 2, then we can kind of succinctly define loop number 3 to just be really both loops, kind of like a wedge sum. So, let's see. And again, the pods, so we said this whole business of like Bn, but like this could be a negative integer, in which case we would just switch the direction. Note that forming sums of loops, we produce loops that pass through the base point more than once. This is one reason why loops are defined merely as continuous paths, which are allowed to pass through the same point many times. So if one is thinking of a loop as something made of stretchable string, one has to give the string the magical power to be able to pass through itself unharmed. However, we must be sure not to allow our loops to intersect the fixed circle. A at any time, otherwise we could always unlink them. Next, we will consider a more complicated linking called the Borromean rings. And basically, I think the thrust of this, without reading the whole paragraph, is that I guess no, they does do ellipses. I knew. Sorry, that was like I was having a whole pain point the other day in a seminar where I was like really trying to get the loops to like be ellipses and they wouldn't be, and it's probably the happiest anybody's been about that feature. Um, but basically, if we have this is a let me color these loops. This is probably like my favorite part of this app, so that I can. Oh, that's a nice color. Hold on, let me add that to my palette. What's a color? I don't really like this red. I'm gonna add that blue. That's awesome. Okay. A, and then B and C. This can be deformed into A and B, and then C is going to do something weird that I'll draw. So C ends up looking like if we make our base point here, C ends up looking like, oh wait, nope. Wait, that is supposed to be clearly under. Yeah, okay. And the orientation is that way. And so, keeping this color coded, but also labeled, these are called the Borromean rings. And the interesting feature is that if any one of the three circles are removed, then the other two circles are not linked. This is where if I had a rope, it would be maybe a good time to use it. But, like, if you kind of look at this, my drawing isn't great. Um, but it becomes pretty clear that if B were not there, then the two ends of C would kind of fall apart and fall through the center of A. Similarly, of course, if C isn't there, then A and B aren't linked. In the same spirit as before, let us regard one of the circles, say C is a loop in the complement of the other two. We will ask whether or not C can be continuously deformed to unlink it completely from A and B, always staying in the complement of A and B during the deformation. We can redraw C. Hold on. We can redraw the picture by pulling apart A and B, dragging C along, and then we see C winding back and forth between A and B, as shown in the second figure on the right here above. In this new position, if we start at the point C indicated by the dot and proceed in the direction given by the arrow, then we pass in the sequence forward through A, measure it forward through B, backward through A, and backward through B. And so if we are measuring the linking of C with A and B by two integers, then the forwards and backwards cancel and both integers are zero. So C is not linked with A or B individually. To get a more accurate measure of how C links with A and B together, we regard the four parts as an ordered sequence. Taking into account the directions in which these segments of C pass through A and B, we may deform C to the sum A plus B minus A minus B. We write the third and fourth loops as the negatives of the first two since they can be deformed to the first two, but with the opposite orientations, as we saw in the preceding example, the sum of two oppositely oriented loops is deformable to a trivial loop, not linked with anything. So we would like to view the expression a plus b minus a minus b as lying in a non-abelian group so that it is not automatically zero. Changing to the more usual multiplicative notation for non-abelian groups, this is what we would write as a, b, a inverse, b inverse, which is the commutator of a and b. And maybe I'll just write that as its own thing. So commutator. And so marking explicitly what we're calling a and b here. So a is going under a in the positive direction. B is going in the positive direction this way. So A goes here, B goes here. But then going over the top of A, going into A, is minus A. And then going similarly this way is minus B. And so all in all, we end up with kind of this non-abelian structure, I guess. So the circle C can be deformed into a certain position that is a little bit more complicated to draw, where it represents the composite loop of the commutator, where A and B, lowercase, are the loops linking capital A and capital B. From the picture on the left, it is apparent that C can actually be unlinked completely from A and B, in which case the commutator is trivial. So the commutator of the fundamental group is trivial if and only if it doesn't have intrinsic linkage. The fundamental group of a space will be defined so that its elements are loops in X starting and ending at a fixed base point, but two such loops are regarded as determining the same element of the fundamental group if one loop can be continuously deformed to the other within space X. In the first example, X is the complement of the circle A0, while in the other two examples, X is the complement of the two circles A and B. In the next section where we construct this, we will show that the fundamental group of the complement of the circle A in the first example is infinite cyclic with loop B as a generator. This amounts to saying that every loop in the complement of A can be deformed to one of the loops Bn, and that Bn cannot be deformed to Bm if n is not equal to m. Huh. That is a really interesting way to think about it. The fundamental group of the complement of the two unlinked circles A and B in the second example is the non-abelian free group on two generators, represented by the loops A and B linking A and B. In particular, the commutator AB, A inverse, B inverse is a non-trivial element of the group. The fundamental group of the complement of the two linked circles A and B in the third example that I didn't draw is the free abelian group on two generators, represented by the loops A and B linking A and B. So as a result of these calculations, we have two ways to tell when a pair of circles A and B is linked. The direct approach is given by the first example, where one circle is regarded as an element of the fundamental group of the complement of the other circle. So, okay, this is interesting. So, okay, two ways to tell if two circles are linked. Where one circle is an element of pi 1, the fundamental group, of other circle. And then the second option is one distinguishes a pair of linked circles from a pair of unlinked circles by the fundamental group of their complement, which is abelian in one case and non-abelian in the other. So distinguish a pair of linked circles from a pair of unlinked circles by pi 1 of their complement. Number 1 is abelian. Number 2 is not. This method is much more general. One can often show that two spaces are not homeomorphic by showing that their fundamental groups are not isomorphic, since it will be an easy consequence of the fundamental group that homeomorphic spaces have isomorphic fundamental groups. Yeah, makes sense. Okay, so on to actually constructing this rigorously. I guess all of this can be thought of as motivation. Yeah. So this section within 1.1 is called paths and homotopy. And let me just see how far I had wanted to get through this, just so that I don't like overshoot or undershoot. So I wanted to get to page 34. Oh yeah, we're doing good time for that. So yeah. So the fundamental group will be defined in terms of loops and deformations of loops by a path in a space. A path in the space X is a continuous map f from I to X. And so then a homotopy, a path homotopy a path homotopy in X is a family f sub t from I to X, where the endpoints f of t of 0 is equal to x naught, and f of t of 1 is equal to x1 are independent of t. And then the associated map f from, I cross I to x, defined by f of s comma t is equal to ft of s, is continuous. And so two paths are said to be homotopic if they satisfy this condition. I just need to blow my nose real fast. Okay. Um, yeah. So the idea here is that we are indexing the family of loops with T, and then we are indexing the actual path itself with S. Um, or maybe it's the other way around. Yeah, so as an example of this that will make the notation clear, a linear homotopy or a straight line homotopy is basically f of t of s is equal to 1 minus t f naught of s plus t f of 1 of s. And so this is kind of our example for if we have two curves, maybe then for any point we can just drop a straight line down. Like so. And so in between, of course, at each time t, you have a different path between the two. I'm actually curious if I can animate this in Desmos real fast. Because Desmos definitely has like the capability to do it. So we'll just use x squared and the constant function 0. Well, I guess that's not very interesting, is it? Let's do x cubed and x squared. Um, so f naught of x is equal to x squared, and then f1 of x is equal to x cubed, and then f of x is equal to 1 minus t f naught of x plus t f1 of x, and then we'll let t oh, I guess we need to put we need to put t within certain bounds. So 0 to 1 in steps of 0.01 ought to do it. Oh yeah, this is awesome. Okay, that's really cool. So let me screen share. Let me switch the screen share. I don't know. I mean, I guess it's kind of. Oh, hello. I'm big. Can you see that? I don't know if you can see that. Hold on. That's a problem. Let me just share my screen. There we go. Yeah, so if we do this, like we can see that. Or maybe we'll pick something more interesting than x cubed, maybe like sine x. Right? Um yeah. I mean like it's simple, right? But like I don't know, that's kind of cool. Especially like I don't know. I bet there's a ton of cool math that comes out of the family of like the family of maps between the two. I kind of wonder, like, let me try. Wait, that was cool. That's a neat function. I mean, makes sense, but okay. I need to like stop watching this because I'm gonna get totally distracted. We have fun around here. Okay, share transcript without audio. Um, Maybe I'll show that to like my family or something. So there was like, asking nice questions. So for a convex subspace, all paths in X are homotopic. So basically, the linear homotopy, the straight line homotopy, makes all paths in a convex space homotopic. So like a corollary, all paths in a convex space are homotopic. Um, so, there we go. So as a fast proposition, um, so the relation of homotopy paths with fixed endpoints in any space is an equivalence relation. So the relation of homotopy on paths with fixed endpoints is an equivalence relation. So reflexivity is given by the constant homotopy. Everything else, there's like a way to speed up the homotopy. And I'm kind of wondering, like, if you have something like I kind of wonder if we were to pick like cosine x and sine x. Or you have fixed endpoints in the y domain. Yeah, like those are clearly homotopic paths. In case you're wondering, yes, I'm looking at Desmos right now. So anyway, try out the Desmos example with sine x and cosine x. It's a neat little picture. Yeah, the equivalence path of a path. Sorry, the equivalence. That's a class or path. This is what I mean when I said I feel like not doing this today. I'm like just tired. I feel like I'm saying stupid things. But anyway, yeah. Basically, we'll denote equivalence classes by F, like so. Um, so defining composition, path composition. So given F and G from the unit interval to X, with F of 1 is equal to G of 0, then there exists a composition or product path, but I'll probably just say composition. F composed with G, which first traverses F and then traverses G. We're basically F composed with G of S is equal to F of 2S or G of 2S minus 1, where 0 less than S less than 1/2, and 1/2 is less than or equal to S is less than or equal to 1. And so this kind of like speeds up the like how fast we go through the homotopies by 2. And I'm sure there must be like something neat about the density of R specifically that makes it so that like we still get the same family of homotopies. Because I guess like the picture would be like if you had, you know, x naught, x 1/2, and then like x1. The idea is that you like, if these are your f stuff, like f1 and f2, and then g1 and g2. Or I guess it's 0 to 1, whatever. Ooh. There we go. Right, and so like the homotopy first kind of looks like this. And then it looks like this. I gotta say, there's much cooler pictures in algebraic topology. Like, it's very relaxing. Um, anyway, yeah, so this is kind of the picture for composition. In particular, we pay attention to paths with the same starting and ending point. And such paths are called loops, and the common point is called a base point. And the set of all homotopy classes of loops, so definition, the set of all homotopy classes of loops based at x naught is pi 1. Homotopy classes of loops at x1, noting that if you have a connected space, then like this is, it doesn't matter where x naught is. And I wrote x1. I don't know why. There we go. And pi 1 is a group, and pi 1 is the fundamental group. So way to like kind of not say everything up front. But yeah, this is a group under the product f g is equal to f composed with g. And this makes a lot of physical intuitional sense. Yeah, so this is the fundamental group of x. So fundamental group of x. And so, yeah. We will see in chapter 4 that this is the first in a sequence of groups pi 1 through pi n called homotopy groups, which are defined in an entirely analogous fashion using the n-dimensional cube in in place of I. And so kind of the way I've heard it explained is that like pi sub I is like an n-dimensional whole. Chapter 4, I don't know. Yeah, it's the section on cohomology. And as cool as I think cohomology is, I don't honestly think I'm going to get there in Hatcher before next term starts. But I do kind of want to keep this up. Like, I would love to have just time to do something like this, maybe in the evenings, or maybe I'll get up early to keep going through Hatcher and stuff, because I really feel like it's just kind of broadening how much math I know, or at least have been exposed to. Maybe know is definitely a strong word, but how much math I've been exposed to. It's never a bad thing to do more math. Yeah. So, proving that the fundamental group is a group, it's a very long thing. Takes up about a page, which for Hatcher is pretty long. I've done this in my topology class, and I don't really feel like redoing it because it's just like a group theory proof. But there are some interesting definitions that come about through it, and so I will define some things from the proof and then just move on with my life. So a reparameterization of a path F is a composition F phi, where phi is from I to I, is a continuous map with phi of 0 is equal to 0, phi of 1 is equal to 1. So reparameterizing a path preserves its homotopy class since we're not changing anything fundamental about the thing. But it kind of allows us to move the curve, I guess, is maybe the thrust of this. So since I guess, okay, another important thing. So an inverse path, an inverse path from x1 back to x naught is defined by f bar of s is equal to s evaluated 1 minus s. That makes sense. I mean, these are kind of geometric constructions in a way, more than anything else. This is notably like an inverse in the group sense as well, because you can compose f with f bar and you just get the constant map at x naught, right? So yeah. So as an example of a fundamental group, we have for a convex set x and r n, so x and rn. Wow, that was a horrible r in rn convex. With base point x naught. We have that pi 1 of x, nope, evaluated x naught, is equal to 0, the trivial group, because any two loops can be contracted back to the base point. And this is something that hopefully just makes a ton of sense because the straight line homotopy kind of lets us map things to constant functions, and then constant functions are contractible back to the identity map on x naught. So, it's not so easy to show that a space has a non-trivial fundamental group since one must somehow demonstrate the non-existence of homotopies between certain loops. We will tackle the simplest example shortly, computing the fundamental group of the circle. So, yeah. It is natural to ask about the dependence of pi 1 on the choice of the base point. And basically it's not. I was looking at it, I was like, I'm pretty sure it's not, right? Like, as long as you have a connected space, it should be fine. So yeah, proposition. The map beta of h from pi 1 at x1 to pi 1 at x naught by beta h of class f is equal to the class H composed with F composed with H inverse is an isomorphism of groups. And so this basically just works with the nice property of like conjugation. So, oh, I guess I don't have my Artin videos up here, but yeah, Artin has some nice stuff about like conjugal subgroups and stuff. How groups act on each other, how groups act on a set, stuff like that. But yeah. So if X is path connected, the group pi1 based at X naught is up to isomorphism independent of the choice of base point. At this point, we usually just say pi1 of X, just because X naught doesn't matter. So a space, to generalize these well-behaved spaces, a space is called simply connected if it is path connected and pi1 of X is the trivial group. So a resulting proposition is that a space X is simply connected if and only if there exists a unique homotopic class of paths. Class of paths connecting any 2 points in X. Yeah, so direction 1 is its trivial group is 0, and we're done. Direction 2 is we have one homotopy class, and so then any other thing falls into that class, and so it's the trivial group, and then every 2 things are homotopic, so they must be simply connected. So yeah, moving on to our next section. So pi1 of the circle. I think I want to get through the next 5 pages, which will put us pretty well. Oh, that's interesting. Okay, so in this thing, we're going to talk about the fundamental theorem of algebra. We're going to prove it with the fundamental group of the circle. That's pretty cool. So yeah. Then we'll get to Borsuk Ulam. There we go. Okay. Yeah, so our first real theorem will be the calculation of pi1 of the circle, which is that that this is isomorphic to Z. Way to give the punchline, dude. So theorem, the map phi from Z to pi1 of the circle, sending an integer n to its homotopy class of the loop I guess we'll say S1 based at the point 1 comma 0, where is an iso, where omega n of s is the unit circle cosine of 2 pi n s and sine of 2 pi n s. And so the general idea here, as like a picture, is that this is kind of all of the branch cuts of a circle. Kind of like so. So like we can just look at the principal branch, or we can look at like, you know, the actual meat of the thing in higher space. This is a very intense proof. This is a 3-page proof. Okay. All right. Well, so the idea is to compare paths in the sphere with paths in R via the map. So let me write proof. Consider P from R to S1 given by P of S is equal to, well, this exact thing minus N. So I'll just copy and paste it. So this could be embedded in R3 as the picture I drew up here. Which sends, so it can be embedded by the same thing with an added coordinate of S. And so then P is the restriction of the helix of this projection onto R2. And so observe that the loop omega n is equal to the composition P omega n, where tilde omega n is from I to R, is the path omega n bar of S is equal to ns, starting at 0 and ending at n. And so we wind around P absolute value of n times, and then going up if n is greater than 0, down otherwise. And so Wn omega is called a lift of omega n. So the definition of phi, which is the thing we're trying to show as an isomorphism, can be reformulated by setting let phi of n be equal to the homotopy class of p f tilde for every path f tilde from any path in R from 0 to n. Such an f tilde is homotopic to omega n tilde by the linear homotopy. So f tilde is homotopic to omega n tilde by the homotopy 1 minus t tilde plus t omega n tilde. So pf tilde is homotopic to pwn tilde, which is homotopic, or which is equal to omega n. And so the new definition agrees with the old one. No, we are still working on the same proof. So to verify that it's a homomorphism, verify that phi of n is a group homomorphism. Let tau m define from R to R be such that tau m of x is equal to x plus m, then omega m tilde composed with tau m omega n is a path in R from 0 to m plus n. So phi of m plus n is the homotopy class of the loop on the circle that is the image of this path under P. This image is just Wm Wn is equal to phi of m phi of n. Okay, so now we want to show that it's an isomorphism. So we need to show injectivity and surjectivity. There is no way. Okay. Surjectivity is easy. Surjectivity takes a paragraph. Injectivity apparently takes 2 whole pages. What? There is just no frickin' way. Maybe he's just like building up firepower for something else. I refuse to believe that an injectivity proof takes 2 pages. Okay. So to show that phi is an isomorphism, we need two facts. So for each path f from I to the circle, starting at x naught on the circle, and each x naught tilde in the inverse image of P, there is a unique lift, F tilde from I to R, starting at x naught. Yeah, I just know, like, I need some homework problems to work through because I would not be able to sit down and do this. And then, I guess for each homotopy, f sub t from I to the circle, starting at x naught. Oh no, for each homotopy of paths, starting at x. Oh no, it is at x naught. And each x naught tilde in the inverse image of x naught, there is a unique lifted homotopy, ft tilde from I to R at x naught. Before proving these facts, let us help see how they imply the theorem. Okay, I knew it was not a two-page injectivity proof. So to show surjectivity, there we go. I did spell it right. Let f from I to S1 be a loop at the base point 1, 0, representing an element of pi 1 of S. By fact A, there is a lift f tilde at 0. F tilde extends or ends at some integer n. Ends at n in Z, since P of the lift of 1 is equal to f of 1 is equal to 1, 0, and P inverse of 1, 0 is equal to Z contained in R. This makes a lot of sense because recall that really P is this kind of helix thing. So like naturally we get Z out of this. Oh yeah, okay, that now it's starting to make sense. That like one thing just made it click for me. Because you can wind, oh my goodness gracious. Okay, yeah. Okay. Then by the extended definition, Phi, we have that phi of n is equal to the equivalence class P of the lift, which is equal to F. And so basically phi is surjective. We get one of these for each such lift n. So for each wind, like we get that. That made so much sense. That's awesome. Okay. And then to show injectivity, so given a map, no. So let 5m equal 5n, then we want to show that m equals n. Well, we know that omega of n is not equal, but is homotopic to omega of m. And so let ft be a homotopy for f naught to f1 by fact b, which says that we have a unique lifted homotopy. We can lift this homotopy to ft tilde. At 0. And so the uniqueness part, by uniqueness of part A, implies that F naught lift is equal to omega m lift. And then F1 lift is equal to Fn lift, or Wn lift. And then since Ft is a path homotopy, the endpoint Ft lift 1 is T independent. So for T equals 0, the endpoint is M, and for T equals 1, the endpoint is N. But since it's T invariant, we get that M is equal to N. So now we haven't actually proved these two facts, and so even though we have shown that phi is an isomorphism, phi is an isomorphism if fact A and fact B are true. And this is the rest of it. So he says that both statements can be deduced from a more general assertion. Just kind of want to look at something real quick. Okay. So, so to prove part A and B, given a map F from Y cross I to the circle and a map F tilde from Y cross 0 to R, which lifts F restricted to Y cross 0. Then there exists a unique map F tilde from Y cross I to R, lifting not the right letter, lifting F and restricting it to the given thing at Y cross 0. So given a map from the space and the unit interval to the circle and a map from the base of this, which is basically just Y, which lifts this thing into R, then we have a unique lift from the disk into R and restricting it to the other lift. Okay, like that's pretty reasonable. Um, hmm. How does this imply the whole thing of A and B? I don't really want to go through proving it because it's very long and it's just an open cover proof. And so it's basically you take an open cover, you pass it through a projection map, you show that that covers a space, and so on. The uniqueness part takes like a paragraph, but otherwise it's pretty standard. Although I do feel like maybe I'm kind of bumping it too hard for how long it is. Um, so statement A is the special case where y is a point, and then B is obtained by applying this thing that we just wrote out, with y is equal to the unit interval I. And then we use the open cover bit. So I'm just going to put dot, 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 box. So some applications of the theorem that the fundamental group is a circle. Proving the fundamental theorem of algebra. So theorem every non-constant polynomial with coefficients in C has a root in C. So the proof is let Z be a formal or let P be a formal polynomial of the form I equals 0. That's terrible. Oh, they really just do that. Yeah. So 0 to n of a sub I guess it would be n. It's gonna be too hard to do this with. They want it to Hatcher wants it to be like zn plus a1 zn minus 1 plus an. So it's monic, right? It's monic and the indices suck. So assume that P has no roots in C. Then for every real number in R greater than or equal to 0, the formula FR of S is equal to P times R e to the 2 pi is what divided by P of R times the absolute value of P of R divided by the absolute value of PR to the 2 pi is. Defines a loop in the unit circle S1 and C based at 1. So as R varies, f of R is a homotopy of loops. So, oh, that does make sense. So as R varies, FR is a loop homotopy. Damn, that does make sense. And based at 1, of course. So since F naught is the trivial loop, meaning that we just end up having 1. Yeah, so yeah, because FR of 0 is equal to 1. Or F0 of S is equal to 1, my bad. We can deduce that the class of FR is in pi 1 of S prime is 0 for all R. Hold on, how is that? I see that it's in pi 1. I see. What? Okay. What does this look like for R not 1? Let me I'm gonna go to Desmos real quick, and if it's interesting, then I'm gonna screen share. But otherwise, I'm gonna not. So let's pick an uninteresting. So p of x is maybe equal to like x squared. And we're gonna just turn off. Yeah, okay. And so then fr of s is equal to p of r e to the 2 pi I s. I guess I should use x. Divided by p of r. And I'm suddenly realizing that Desmos doesn't do complex functions. Desmos complex plane. Okay. Oh, it wants me to parameterize it. I don't want to do that right now. Okay, hold on. Then maybe we can just graph this by hand. For context, the thing that's throwing me for just a total loop is I can't get how the loop action contracts for R non-zero. You get we have no roots, so we don't ever get P is 0. So then if we have P of this thing, then we get some branch of S. Well, the unit circle of radius r. So we get some complex number in here. So P of some complex number is in here and in here. We have no roots, so this should never be 0. And it's just of radius r. But how does that contract back? I guess C is convex. Is that how? C is convex, so we just always contract back to the circle? And then if P of R does have a point, then it has a non-trivial fundamental group identification. That's how. Okay. It's coming together, slowly but surely. Okay, so now fix R greater than the sum I equals 1 to n of absolute value of AI. Um, Greater than 1. Then for the absolute value of z is equal to r, we have that z to the n is equal to r to the n is equal to r times r to the n minus 1, which is greater than z to the n minus 1 absolute value times the sum I equals 1 to n of absolute value of an, which is greater than or equal to a1, no, a1 z to the n minus 1 plus dot 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 plus presumably all of these. So, okay. I have no clue where the stuff in orange is coming from. This just seems like a totally random choice. Um, I don't like analysis showing up in a class that has algebra in the name. Um, okay. So from this last inequality, it follows that the polynomial p t of z, pt of z, oh, which is equal to z to the n plus t a1 z to the n minus 1 plus an has no roots on the circle z absolute value is equal to r. For t in 0 to 1. It's strictly greater than. Wouldn't it all have to be negative for this to make the point that it's trying to make? Wouldn't it have to be minus t? Why is it not minus t? Okay. I'm not really sure why they're making this choice, but I guess the idea is like if this right hand portion isn't negative and Zn is positive, like we're not gonna intermediate value theorem ourselves out. So okay. Replace P for PT in this formula, which I'm not rewriting, so I'm copying and pasting that. And let, oh, nope. Yep. Wait, hold on. Yeah. Then we have a loop homotopy from this loop. Then there exists a loop homotopy from FR of S to omega n of S, which is equal to e to the 2 pi I and S by theorem 1.7. What the hell is theorem 1.7? Oh, the theorem that we spent so long proving that the fundamental group of the sphere is Z. So, wouldn't have been that hard to say that. Since pi 1 of S1 is Z, omega n is n times a generator of the infinite cyclic group pi 1 of S1, which is really NZ. And so then omega n is equal to FR is equal to 0. Implies that n is equal to 0. So the only polynomials without roots are constants, right? That actually, okay, that is really clean. Just a little exposition would have gone a long way. I don't even know if I really feel like I get it. But you know, it's okay. It'll be fine. I'm kind of tuckered out. Um, I don't think that if I keep going, I'm gonna absorb anything. And so I'm going to take this opportunity to say we proved a big theorem. We covered a lot of material. We introduced going from loop homotopy to the fundamental group to proving a pretty big algebraic result with loop homotopy and with the fundamental group of the circle. So I'm pretty happy. I think that's a lot for just one lecture. Thank you so much for watching. I hope if you did watch all of this that I didn't do anything terribly wrong. And if I did, please comment below so that I can learn better. Yeah, have a great day. See you next time.